Hello, Surya, are you able to hear me?
ఎస్ సార్ వినిపిస్తుంది సార్.
ఏంట్రా క్లాస్కి అటెండ్ అవ్వట్లేదండి మిగతా వాళ్ళు నిన్న అంతే వచ్చారు ఈ రోజు అంతే సగం మంది వచ్చారు ఏంటి
సార్
సప్లిమెంటరీ
ఇప్పుడు ఎగ్జామ్ జరుగుతుంది కదా సార్, సప్లీ ఎగ్జామ్.
సప్లీ 30% 50% మెంబర్స్ సప్లిమెంటరీ ఎగ్జామ్స్ ఉన్నాయా?
అంటే సార్ ఎమ్1 కదా సార్ ఇవాళ.
ఆహా. ఎక్కువ మందికి అమౌంట్ ఉందా?
అవును సార్.
ఓకే రైట్ సో విల్ స్టార్ట్ టుడేస్ క్లాస్. Okay, so I think my screen is visible to you, right? My presentation is visible to you, right?
Yes, sir.
Okay, right. So in the previous class, we discussed about design of welded joints when they are subjected to eccentric load in the plane of the weld. When you have a eccentric load in the plane of the weld is subjected to two shear stresses, namely direct shear. First one is direct shear or primary shear stress. The second one, because of the torsion moment, because the eccentric load is in the plane of the weld, it will create a twisting moment in the weld. So because of that, you have a torsion shear stress. That torsion shear stress, we name it as a secondary shear stress. So based on the primary and secondary shear stress, we see how to design the welded joints. Now, if the weld is again here, the second case is also welding joint subjected to eccentric loading. But here there is a primary stress or primary shear stress. Direct shear stress will be there. But the second one, that is in earlier case, the movement is a twisting movement. When the load is in the plane of the weld, your resulting effect of that load is going to be a twisting moment in case of the previous case. Now we will consider when the load is creating a bending moment in the weld, how we can design that. So same thing here also, it is eccentric load. Only thing is here the eccentric load will create a direct shear stress plus a bending stress, whereas in case of previous case, that eccentric load is creating a direct shear stress plus a torsional shear stress. So that means the secondary stress is different here. In this case, it is a bending stress. In the previous case, it is going to be a twisting or torsional shear stress. So now, if the load is creating a direct shear stress and a bending moment, how we can design the welded joint? So that we will see now. So like this here, for example, if you consider a cantilever beam. So cantilever beam means one end is fixed, other end is free. So I have a rectangular cross, this beam having some rectangular cross section. So you can see the cross section here, it is a rectangular cross section. So now this plate is welded to this wall by two weld joints. So he has given the fillet welds, their designation as W1 and W2. So here it is W1, top weld is W1 and bottom weld is denoted as W2. So now if you see here, your loading direction is something like this, but the length of the weld is going to be like this. That means if I assign the axis here, of course, here it is given here something like this. Now XY plane is going to be your welding. So our plane of the weld, but the load is acting here in y direction. You can say it is acting in y direction, but the length of the weld, so is going to be along this axis. That means here this is going to be somewhat transverse to this length of the weld. So in this case, the resulting effect of this eccentric load is going to be a bending moment. So if not, okay, it's not a twisting moment, it is going to be a bending moment. So that's what he described in this slide. So the eccentric force P can be replaced by an equal and similarly directed force P acting through the plane of the welds along with a couple. The couple magnitude is MB is equal to P into E as shown in figure. So anywhere in the previous case also the same thing. we have an eccentric load, we replace that or we transfer that eccentric force to the centroid of the weld. So by doing so, in the previous case, when the load is in the plane of the weld, the eccentric load will be replaced by a direct force P and a twisting moment P into E. Now here, because your weld length direction is something like this, so if you transfer the same force P to the CG of the weld, here also again the same thing. The result is will be a direct force P and at the same time a couple of magnitude M into E. But this couple will going to create the bending moment or bending stress in the weld. Whereas in case of previous case, it is a twisting stress, torsional shear stress. Now here it is a bending stress. So that's what it is illustrated in this figure. See, this is the actual case. So now if I transfer this eccentric load through this G, center of gravity of the weld here, the net effect is a direct load whose magnitude is equal to P itself, and in addition to that you have a movement, a bending moment which is MB, or couple I can call it as, since it is a bending moment, it is denoted by MB, and the magnitude of that bending moment is going to be P into E. So direction, you can easily identify the direction of that movement also here. So here if I take moment of this force about this G, so this is the direction of the force and this is the perpendicular distance. The magnitude is going to be P into E, and about this point G, this P will create a clockwise movement. So that's why it is shown as a clockwise movement also here. Suppose if you have the load, maybe obviously if the loading condition is something like this, it will be like this only. You have in this direction you have a plate, and if it is applying something like this, then you have a anti-clockwise movement. Here you need to consider something like that. So anyway, here, so that means, so in the first figure what you have seen is the eccentric load is there, the eccentric load is transferred to the centroid of the weld. So the net effect is going to be a direct force and a bending moment. So now, since you have two loads are there here, one direct force and one bending moment, so we'll use the principle of superposition to find out what is the effect of those individual loads. Then finally, we'll using that principle of superposition, we'll find out the net effect or resultant effect. So for that here, this is equal to, so principle of superposition is nothing but only thing is, so two loadings here, we are splitting these two loads into two loading scenarios on our welded joint. So that is, one is purely that load P, only this one we will consider, that is that one, plus then only the pure bending moment. So we have only pure bending moment. So therefore, because of this direct force P, what is the magnitude of stress induced in the weld? You need to compute that. Then similarly, because of this bending moment, what is the magnitude of the magnitude of the stress which it is going to induce in the weld? So here you can clearly see that this P is going to be a transverse force. So a transverse force will create a shear stress in the weld. So the magnitude of the shear stress is nothing but load, that is P, divided by area of the weld. So you will get directly similar to your previous case. So direct shear stress or primary shear stress is same. As long as you have an eccentric load, the first stress it is going to induce is a direct shear stress whose magnitude is P by A. That is same in both the cases. Only thing is the second, that is the secondary stress, is going to be different. Here it is a bending stress. In case of the previous one, it is a torsional shear stress. That is the only thing. So now, if I consider the second one, it is weld subjected to a bending moment. So I know the bending moment. If I know the bending moment, using your bending equation, you can calculate the bending stress. That is MB by I. M by I is equal to sigma by Y. So this is your bending equation. Using this bending equation, you can calculate the sigma, where sigma is the bending stress. Generally, it is a normal stress. That's why we'll use sigma symbol for bending stress. Whereas in case of shear stress, we'll use tau. So, or else if you want to denote it as bending stress, you can take sigma B also. So anything is okay. So that means here, again, if you look at this formula here, or if I rewrite this formula, from this, I can get sigma B is nothing but M by I into Y. So M is for a given welds, or for a given load and eccentricity, M is constant, and I is also constant for a given cross section of the weld. Then only the magnitude of sigma B will depends upon Y. So that means Y is nothing but the distance of the point from the center of gravity of the weld to the point what you are considering on the weld section. So here something like, if I take the cross section here, so here if you consider this is the point, this is going to be the Y distance. So if Y increases, the bending stress will also increases. So that means, since always in design we will design for the maximum stress, you need to choose the maximum value for this Y. So if you choose maximum value, so you will get maximum bending stress. So that is the criteria for the designing the weld joint. So I know the direct shear stress, I know the bending stress. Then how I can club these two? That is, one is a shear stress. Because of this P, you have a shear stress. Because of bending, you have a normal stress. In the earlier case, both are shear stresses. Primary, that's why we name it as primary shear stress and secondary shear stress. But here, one is shear stress, other one is a bending stress. So how I can club this so that I'll get the net effect. So again, to do that, what we'll do is we'll use the failure theories. So in the beginning, we discussed about the static failure theories. So we need to use those static failure theories in order to find the net effect of these loads. So that means if you know how to calculate the principal stresses, or if you know the formula for the principal stresses, so like I already told, we'll use failure theories. So for that, if you go for maximum principal stress theory, so I have a one normal stress, one shear stress. I can calculate what is the principal stress. If I use the formula for the principal stresses, I can calculate the sigma 1 and sigma 2. So then from our design point of view, if that sigma 1 is less than the allowable normal stress, so that is in the limiting condition, your sigma 1 should be equal to the allowable normal stress. So that is going to be what is an equation. Or else sometimes, what we discussed in the earlier classes, this maximum normal stress theory is applicable for only brittle materials. Suppose if you want to design based on the shear stress, so that means if you want to use either distortion energy theory or maximum shear stress theory, how we can club this, or how we can find the net effect of these two stresses in terms of a shear stress. So for that, what you have to do is, like how you are calculating the principal stresses, you need to find out what is the maximum shear stress. For that also you have a formula. So principal stresses you have a formula, for maximum shear stress also you have a formula. Using that formula, we'll calculate the maximum shear stress, and then we'll equate this maximum shear stress to the allowable shear stress in the weld. So from that you will get the weld dimension. The only thing is, what we need to do is, we need to find out what is the size of the weld here, if it is a design problem. Or else, in otherwise, if I already given the size of the weld and he has given the load, he will ask us what is the maximum stress in the weld. So either way, the question may come, whether it may be in the form of analysis problem or it may be in the form of a design problem. Okay. So this is what is the basic procedure what we need to follow in order to design a welded joint which is subjected to bending moment. So and also one more thing here is, in order to compute the bending moment, what you require here is, you require I. I is nothing but area moment of inertia. Or else, if I go for this formula here, if I arrange these things, okay, so whatever formula written here for the bending stress, so M by I into Y, or else if I take these two terms, I by Y, here I divided by Y, I'll take that one as a section modulus. So your Z, which is divided by Z, which is nothing but I divided by Y. So that means I can write bending stress expression also something like this, M by Z or MB by Z, where MB is the bending moment given by this formula P into E, and Z is the section modulus. So now, like what we discussed in case of the previous case, here also the section modulus you can easily calculate for a regular sections. But here you have a weld sections are there. So again, to compute the Z value for the given weld section, what you have to do is you have to use you have to pick the formulas from the data book here again. So already shown to you in the previous class. So for each cross section in that data book, he has given what is the section modulus and what is the polar moment of inertia. So in the previous problems, we use polar moment of inertia because it is subjected to a torsion stress. So we require the polar moment of inertia. Now here it is subjected to bending moment. So now you need to pick the formulas for the section modulus. So the same tables. So in the table you have to choose the formulas for the Z, which is nothing but the section modulus of the weld. So here always it need not be the cross section. Weld section will be something like this. Here it is something like this. Sometimes you may have a circular section also, something like this. The weld will be something like this, or maybe some other different section. So whatever may be the section, for all those sections the formulas are available in the data book. Or if you don't want to use the data book, then what you have to do is you have to use your principles of mechanics to derive what is the section modulus for this one. So either way it is okay. So but you don't know what are the principles and how you can derive all those things. So better thing what you have to do is you have to use the data book. So if you use the data book, directly you can pick the values of Z. Of course, for G, that center of gravity also you need to use the data book to pick the values of or formulas for X bar and Y bar for a given weld section. So you need to use here also data book. So that's why always it is advisable to use data book instead of calculating these section modulus values using the principles of mechanics. So once you done that, so you can calculate bending stress. Direct stress anyway it is going to be load by area only, that you can easily calculate it. So from that we can calculate what is the resultant shear stress. Once you are able to calculate the resultant shear stress, then you need to equate the resultant shear stress to the allowable shear stress. From that you will get your size of the bed. Okay, the same thing what I have prepared in the slides also, I'll show you the same thing here in this also. Okay, so then the force P through the plane of the welds causes the primary shear stress tau1, which is given by tau1 is equal to P by A. So this is what I already told to you. So it is same whether the load is creating a additional bending moment or twisting moment, but the primary shear stress is going to be same, tau1, which is going to be P by A. So P is given to you. You need to compute based on the cross section of the weld here. So you need to compute the area. Suppose I have a rectangular cross section is something like this. Here I have one weld and here I have one weld. So then the area should be, here this length he has given it as B and this one he has given it as T. So B into T multiplied by 2, because you have two welds here. 2 into B into T is going to be the area of the weld. So area I can easily calculate, but only thing is a section modulus and polar moment of inertia, we need to use the data book. Okay, right. So here this is the formula for the primary stress. So I can calculate from the given P value and A value, I can calculate this tau1. Then we need to go for bending stress. The moment MB causes bending stress in the weld, and the bending stress is given by the formula. Just now already told, sigma B is nothing but MB into Y by I. Or you can derive this I by Y as a section modulus also, where I is moment of inertia of all the welds based on the throat area, and Y is the distance of the point in the weld from the neutral axis. That's what I said. So this neutral axis will coincide with the centroid of the weld. So you need to measure the distance Y from the centroid or from the neutral axis. Then the bending stresses are assumed to act normal to the throat area. So like I already told, this is a normal stress. The resultant shear stress in the weld can be given by, if you use the principle of, if you use the formula for the maximum shear stress, tau max is nothing but sigma 1 by 2 plus whole square plus or minus plus tau 1 square. So this is the formula. So if you use the formula for the your tau max formula, what is your tau max formula? So if I take it, it is nothing but sigma x minus sigma y by 2 plus tau xy square under square root. So this is the formula for your tau max or maximum shear stress. So now in this, our sigma x is going to be sigma b and sigma y is 0. You have because you have only one normal stress. Sigma y is 0 and tau xy is going to be your tau 1. That is the primary shear stress. So now if I substitute this, what I am going to get is sigma b by 2 whole square plus tau 1 square. So again, this tau is in terms of unknown this throat thickness value, T value. So always, whatever value you calculate, if you compute this tau is in terms of unknown T value. Like in the previous problem, what we have seen, something like a 300 by T, like that you will get. So now, if you take this tau and if you equate this tau to the allowable shear stress, so then from that you will get the value for this T. So this is how you can design a welded joint which is subjected to a bending moment or eccentric loading. So a bending moment due to that eccentric loading. Okay, so quite simple. So previous similar to the previous one, only thing is here the centric load is creating a bending stress. Instead of process stress, it is creating a bending stress. Again, we'll illustrate this procedure through one more example so that you can clearly understand this one also. So first you note down this is the problem what we are considering. So first you note down this problem. I'll give some 2 minutes, 2 to 3 minutes time to note it down. So after that we'll discuss the solution. So in this figure, whatever dimensions are there, you take all those dimensions are in mm. So here this 150 is mm, 100 mm, and 500 mm. So now you note it down. Once it is completed, somebody respond so that we can start the discussion about the solution of this problem. So now you can note it down. Okay, is it over? అయ్యా శివప్రసాద్ నోట్ చేసావా? ఉన్నారా క్లాస్లోనే? త్రీ శివప్రసాద్ మొబైల్ ఆన్ చేసి ఎక్కడికో వెళ్ళిపోయి ఉంటుంది. త్రీ నోట్ చేసావా? అయిపోయిందా ప్రాబ్లం నోట్ చేయడం?
సార్ అయిపోయింది సార్. నోట్ చేసా సార్.
ఓకే రైట్. ఇంకా అయిపోయిందా? ఎవరైనా నోట్ చేయాల్సింది ఉందా? ఇంకా 346
అయిపోయింది సార్.
ఎవరు అయిపోయిందని చెప్తున్నారు? 346
13 సార్.
ఎక్కడ ఉన్నారా బాబు? 3 సార్లు అడిగినా కానీ చెప్ప రెస్పాండ్ అవ్వలేదు నువ్వు.
అంటే ఎవరన్నా ఇంకా ఉంటారేమో అని రెస్పాండ్
నేను నీది అయిపోయిందని అడిగారా? ఇంకెవరన్నా ఉంటారు? 4 మినిట్స్ అడగలేదు కదా. నువ్వు నోట్ చేయడం అయిపోయిందారా అని అడిగా. ఎవడో వాట్సాప్ చేస్తే గానీ మళ్ళీ వచ్చి రెస్పాండ్ అవ్వ, అంతేనా?
లేదు సార్.
ఓకే సాయికృష్ణ అయిపోయిందమ్మా నోట్ చేయడం? రైట్. ఓకే, సో దెన్ విల్ సీ ద సొల్యూషన్ ఫర్ దిస్ ప్రాబ్లమ్ ఆల్సో. Okay, so here is given a beam of rectangular cross section is welded to a support by means of a fillet weld as shown in figure. Determine the size of the welds if the permissible shear stress in the weld is limited to 75 Nm². So here also in this problem he has given permissible shear stress, means you need to calculate the resultant shear stress. Maybe sometimes they may give permissible normal stress instead of shear stress, they may give normal stress also. If that is the case, what you have to do is you have to calculate what is our maximum principal stress formula for sigma 1. So that's what I already told in the earlier discussion. So we know the formula for sigma 1, that is nothing but sigma x plus sigma y by 2 plus or plus square root of sigma x minus sigma y by 2 plus tau y square. So you need to use that formula to calculate sigma 1. But in this problem he has given, since he has given the shear stress, you have to compute the tau max value only. You have to compute tau max. So then equate the tau max to the 75. From that you will get the required thing, that is the size of the weld. So you can calculate the size of the weld. So for that, here the important thing is you need to look at into the cross section. So definitely whenever you have a problem on eccentric load, they will give 2 pictures. So 2 views of that joint. So this is one thing, one view, and this is another view. So the second view will clearly show you what is the section of your weld. So based on that only you can easily identify the properties of this section, weld section. Okay, right. So here in this you have a rectangular plate. This is the plate. It is welded here. So whatever this weld is there, this cross section he has shown it here. So something like a, so the cross, since the cross section of the plate is rectangle, so at the circumference it is welded. So throughout the circumference it is welded to this base. So therefore you got this kind of welded joint. So now this plate is subjected to a force of 25 kilonewtons at this end or at the free end. So then he has given the distance is 500 mm. So the distance between this base to the load, that is nothing but our eccentricity here, which is 500 mm. So coming to the section, here this is 100 mm and the side is 150 mm, yes given. So for this problem, in order to find out the size of the weld, what you have to do is, first you have to compute what is the primary shear stress, and then you need to compute what is the maximum bending stress. So then use that formula what I have already given to you to find out what is tau max, then equate the tau max to the 75, from that you will get the T value. Okay, so this is the procedure. So now I will show you the calculations also. So first you need to, this is the given data, whatever he has given, that is load is 25 kilonewtons and tau is allowable shear stress is 75 Newton per mm square. So whenever load is in kilonewtons, always what we'll do is we'll try to convert that one into newtons. So therefore it becomes 25 into 10 cube newtons. So then first we'll compute the primary shear stress. The formula for primary shear stress is tau 1 is equal to P by A. P is already given, you have to compute A value. So for that, here he has calculated the total area of the horizontal and vertical welds. So here you have 2 horizontal welds and 2 vertical welds. So you have to compute the total area. So now if I take the thickness of the weld is T, then this length he has given it as 100. Even this is also 100. So then this was the horizontal weld. The area of this horizontal weld is going to be 100 into T. Even this horizontal weld also it is going to be 100 into T. So it is 200 into T. Then if I take the vertical weld here, this dimension he has given it as 150. Of course, ఇక్కడ మీకు ఒక డౌట్ రావచ్చు. What is the doubt? ఇక్కడ నుంచి ఇక్కడ దాకా 150 ఇచ్చాడు. But horizontal weld కన్సిడర్ చేసేటప్పుడు we are already consider this limit. We already consider this and we consider this. This is already done. So we are taking this one as T and even this one as T. Then this area is 100 into T and this area is 100 into T. So then ఈ vertical weld area calculate చేసేటప్పుడు ఏంటంటే, then you have to consider actually to be precise or to be accurate, you have to consider only this length. But we don't know that this T value here. So we have to calculate this T value. And also if you compare the value of T with respect to this 150, it is small, then what we will do is, here we'll ignore that and we'll take this height of this weld as 150 itself. So therefore it is 150 into T, even this is also 150 into T. So that means 100 plus 150 into 2 into T, that is going to be the area. So that's what he has shown it here. So 2 because area A is given by 2 because we have 2 horizontal welds as well as 2 vertical welds. So that is why it is 2 here. For horizontal welds, one horizontal weld, the area is 100 into T. On vertical weld, the area is going to be 150 T. So now, if I calculate the total area, then from this, I got it as 500 into T. So here, T is unknown for us. We need to calculate the T. So since all these dimensions are in mm, I'll take T is also in mm, so that I'll get the area is in mm square. So I got the area. I have a P is already given in the problem itself. So that is 25 kilonewtons. So therefore you will get your tau 1. That is the primary shear stress, which is given by tau 1 is nothing but P by A. P is 25,000 newtons and area just we calculated as 500 T. So if you substitute that and if you simplify, you will get your primary shear stress as 50 by T Newton per mm square. Because why the units are Newton per mm square here? Load P is in newtons and area is in mm square. So therefore you will get Newton per mm square. So that is about the primary shear stress. Then you need to compute what is the bending stress also. So the bending stress formula is this one. Like already told, sigma B is nothing but mb by z. So first you have to compute what is mb, that is the bending moment, and what is the section modulus for this weld. So this mb we calculated based on the P value and eccentricity value. So in the problem, if you look at the problem diagram here, you can clearly see P is equal to 25 kilonewtons and E is equal to 500 mm. So if you multiply these two, you will get your mb value. So that's what I did here. So P is mb is nothing but a bending moment, which is nothing but P into E. P is given as 25 kilonewtons. I converted that one into newtons, so it becomes 25,000 newtons. And E, eccentricity, is given it as 500 mm. So if I multiply this one here, I get it as 125,000,000 Newton mm, because this is force P is in newtons and this E is in mm. The resulting units are going to be Newton mm. Okay, I got MB value. But what about Z value? So Z is section modulus. So like already told, you need to pick this formula for the Z again from the data book. So now, if you have data book with you, you open the page number 10.13. So what we discussed in the previous class, same topic, maybe same tables, maybe now the cross section is only the difference. So what I'll do is I'll come out of this presentation mode and I'll take it to the video mode and I'll show it to you where you have that formula also. So in the data book. Okay, so now you can see here, this is the page number 10.13. I think it is okay. So I think it is visible to you. So our cross section is something like this. Whatever he has given, the cross section is something like this. So it is a rectangular kind of thing. So here he has given all the formulas also. You can see that X bar and Y bar he has shown X bar and Y bar. And here he has given the formula for X bar as well as Y bar. Of course, since here it is symmetric, directly you can find out the centroid also. It is X by this height by 2 and this width by 2. So easily calculate the centroid. So that's why I not shown those calculations there. Then we have to use, okay, we need to come to this one here. You can see that here what it is written, section modulus in bending. So you can see that x-axis about horizontal axis x-axis. So this is the horizontal axis. About this axis, he has given the formula for section modulus. Here, this formula is for the polar moment of inertia. What we discussed for the previous type of problem, you have to use this. But here, in case of bending, you have to use the section modulus. So here, what is the formula he has given? You can see that clearly. T into LB plus B square by 3. So that is the formula for the section modulus. In that, what is L, what is B? So you need to know those things. T is anyway unknown. L and B, you should know what is L and what is B. So now, if you look at this diagram here, so this dimension, this horizontal length of the horizontal weld is going to be L, and width, height of the vertical weld, so that is going to be B. So in this formula, only those two things we required. We need to pick those two values from the given problem data. So L is going to be, in our problem, L is going to be 100 and B is going to be 150. So vertical height 150 has given, horizontal weld length he has given it as 100. So if I take that, if I substitute that into this formula, I'll get the section modulus for this weld. So once I have a section modulus, simply I'll use M by Z formula to calculate the bending stress. So to show you that, again I'll take you to the presentation mode. Okay, so this is the formula like what I have shown already to you. So this formula is taken from the data book. So where Z is equal to T into L plus B, L into B plus B square by 3. So where your L is nothing but this horizontal distance, this is 100, and B is this vertical distance, which is 150. So that's what I substitute here in this also. So T is unknown, T will remain as T itself, L is 100, B is 150. So again, plus B square is nothing but 150 square by 3. So if I compute this value, it comes out as 22,500 into T, which is in terms of mm cube. Why it should be in mm cube? You can see that here. This is mm. This is mm. If you multiply these two by mm, you will get mm square. And this even this t is also having a units of mm. So you have 3 mm values are multiplied. So therefore your unit should be mm cube. Okay, so now I know bending moment, I know the section modulus. MB is known to me, already calculated. Z is calculated using the formula from the, by taking the formula from the Z. So then you can calculate now sigma B. So your sigma B is nothing but MB by Z, which is nothing but your MB divided by 20, Z is 22,500 T. If I simplify this, I got it as 555.55 by T Newton per mm square. See here, what primary shear stress is in terms of unknown T. Even bending stress is also in terms of unknown T value. Both, and also one more important point is, while finding out the resultant, always make sure that the unit should be same. Here for this it is Newton per mm square. Even for this also it should be Newton per mm square. You cannot take here some other value, something Newton per meter square or something like that. Then you will get a wrong value. So always the unit should be same in order to compute the resultant stress. So once we have a tau 1 and a sigma b, now I can compute what is the maximum shear stress by using the formula for the maximum shear stress. So that is resultant shear stress, which is given by this formula. Square root of sigma b by 2 whole square plus tau 1 square. So we already calculated sigma b and tau 1. I'll substitute those two values into this formula, which is nothing but for sigma b is 555.55 by t divided by 2 is nothing but you will get 2t whole square plus tau 1 is nothing but 50 by t whole square. So now if I simplify this, I got it as 282.24 by t Newton per mm square. So now this is the resultant shear stress. So now in order to find out the value of T, what you have to do is you need to equate this one to the permissible shear stress. So the permissible shear stress he has given it as 75 MPa or 75 MPa, 75 Newton per mm square. Both are same. You need to equate these two. So by equating this, from this you will get T is equal to 3.76. See, you can see that here the value 3.76 is very small when compared to 150. So like I already told earlier, so you have a confusion here. So to calculate the length of the vertical weld, you have to take only this distance. So that means in this 150 you have to subtract this T and this T. But so before doing that, we don't know what is the formula is. To be precise, you have to take like that only. So if you do that like that, what you will do is you will get some complicated equation. So still you can solve that, but only thing is to reduce that complexity, we ignore the here. Simply by taking the height of this weld as 150 and we solved it. So we got T is 3.76. So if you compare 3.76 with 150, it can be very small or you can ignore its effect also. So therefore, the size of the welds is going to be finally 3.76 mm T. So not its size, it is only T, but you need to calculate the size. So size of the or leg of the weld, the formula for that is root 2 times the throat thickness. So which is nothing but if you multiply root 2 by this 3.76, you got it as 5.32 mm. So this is going to be the answer for this particular problem. Okay, so like this we can solve the problems whenever a weld load which is subjected to eccentric loading. So whether you have two types of problems in this, one type of problem is the weld load is subjected to eccentric load in the plane of the weld, so which will induce a direct and a primary and secondary shear stresses. Whereas in other case there is the primary shear stress and a bending stress is there. So in both the cases we know how to design the welds. So with this we close this welded joints. We completed this welded joint topic. So in the next class, we will try to take up the next unit. I think it may be a bolted joints or maybe the cutter joints. So I need to see the syllabus. So we'll move to the next topic in the next class. So now, if you have any doubts so far in this, we can discuss our doubts so that we can close this topic. So now, you can ask your doubts. If you have any doubts in this, for that matter, not only in this problem, any point or anywhere in the welding problems, If you have any doubt, you can ask. If you don't have any doubts, then what you can do is go to the attendance sheet and respond to that attendance. And then you can leave the class. I think most of you are already leaving the class. Okay, you can leave the class. If you don't have any doubt now, you can leave it.
సార్
చెప్పమ్మా.
సైజ్ ఆఫ్ వెల్డ్ హెచ్ ఈక్వల్ టు రూట్ 2 ఇంటూ టీ అన్నారు కదా సార్. హెచ్ ఈక్వల్ టు రూట్ 2 ఇంటూ టీ అన్నారు కదా సార్.
ఎస్.
అది ఏ వెల్డ్ కైనా అదే ఫార్ములా సార్? అంటే ఇది ఫిల్లెట్ వెల్డ్ కదా సార్ ఇది.
Whatever may be the type of the weld, your relation between root thickness and size of the weld is going to be root 2 times t. Why it is? So if you go back that, we'll assume that weld as a right angle triangle. So from that we derived all these things, right? Okay, I'll show it to you that. The beginning classes. Yes, here you can see that. So your weld generally, a fillet weld will be something like this. See here, this is going to be, we are assuming that one is a right angle triangle having an angle of 45 degrees. So now this is going to be your size of the weld. S is nothing but size of the weld, and this is going to be the T is going to be the throat thickness. So if this angle is 45 degrees, this is the minimum thickness. So we'll consider minimum thickness as the throat thickness. So here this angle is for 90 degrees again here, perpendicular to this. So if this is T, if you want to compute this angle is going to be 45 degrees, or even this is 45 degrees. If you apply that formula, what you are going to get is your S is nothing but T by sin 45. So which is nothing but root 2 T only. So based on this only you got that relation. Clear?
ఓకే సార్.
Right. Any other doubt? Okay. So then, I think most of you left the class. I will also close the class. Only LE8, LE4 are left in the class. Okay, they are also leaving. No issue. I will start the recording first.